All right, welcome to the concurrency video. Before I dive into the concurrency, I'm going to first of all correct something. Okay, not really correcting, but I want to provide a little bit more clarity as to some of the things I did in the error handling video. So the first one I want to talk about is this pipe. So this is called pipe. This thing that looks like a, I don't know, it looks like a pipe. Literally it looks like a pipe actually. So it's called pipe, and then it also used to perform a bitwise OR. So there's something called bitwise OR. This, okay. So we have AND, we have XOR, and all those things. Don't worry about them, but just know that that's what this does. All right. So, and yeah, basically, if you're interested, you can look up bitwise operations. You would see what those do. But for now, don't worry about them. You probably won't even use it in your programs. All right, so that's the first thing. The second thing is I want to simulate a scenario where we actually have an error in our code. So I'm going to remove that flag and try running this code. And yes, we have an error. Panic bad file descriptor. Okay, so this is an error. But where is it coming from? We know that it's coming from here, from this panic, right? But then, which of these errors is returning this for a bad file descriptor? We don't know. So that's why it's generally a good idea to add context to your errors. So how do we do that? We use the errors package that comes with the Go standard library. We can use it to create an instance of an error. So you can see the return type in the function definition. So we can add context to our error by saying errors.new. We go ahead and say an error occurred opening the file. Okay, now we can concatenate our error message. So to do that, we use the plus sign and do error dots. We call the error function. So this would give us a string value of our error message. So remember when I showed you the error interface, it has okay, actually let me open it again. So, or you know what, just it's just basically has only one function method signature, and that is this error. Okay, so luckily our open file function returns an error type that implements the error interface. So that's why we are able to access this error method here. So this should give us the string version of our error message. Okay, so we're going to do the same thing here. So errors.new, you can say an error occurred, write into file. Okay, so we can also concatenate that, do the same thing, error. Yeah, so that looks good. I'm going to go ahead and run that now. So notice that go imports already imported this for me. So as you can see, there's actually a utility that comes with Go called Go imports. Yeah, so this is what your IDE uses to manage your imports, helps you import your packages and stuff. So automatically it does that for me. Once I type the name of the package, automatically my IDE helps me to import them. Okay, so just in case if yours does not, just always remember to come up here and import it manually. All right. Okay, so I'll go ahead and save now and run this code. Yeah, so as you can see, we now have a different error message which says an error occurred writing to file. So now we know that our error is not coming from here but from here. So what could be the problem? We did not pass in the right flag. Okay, so we didn't tell the operating system that we also want a file descriptor that will give us the ability to write to a file. So that's probably why we are seeing this bad file descriptor as part of our error message. So we're going to just pass in that flag right now and try running the code again. Yeah, and everything seems to have worked. All right, so I think that's all I wanted to point out. Hopefully we played around with this and now you are a much better error handler. Okay, so let's move on to what we have today. That is concurrency. What is concurrency? Concurrency is the ability of different parts or units of a program or algorithm or problem to be executed out of order or in partial order without affecting the final outcome. Okay, so concurrency, usually the name sounds like that everything is running in parallel. Okay, say you have multiple tasks and it's happening at the same time, exact same time. This is not what concurrency means. As you can see, there is no indication from Wikipedia that concurrency is something that's happens at the exact same time. All right, so that is not what it is. So but there is a bit of similarities to what parallelism is, which is probably why people are confusing the two terms. Okay, so concurrency is somewhat, I think for me the simplest way to actually explain concurrency is multitasking. Okay, so when you say that, or maybe in your resume you write that you're a multitasker, have you ever imagined yourself multitasking? Okay, so biology says that your brain cannot hold more than one context at the same time. So which means the so-called multitasking is you shifting your focus from one task to another simultaneously, right? Yeah, that is what concurrency is. Simultaneously shifting focus to different tasks. So that is it. So imagine a program that is trying to do many things at the same time. Let's say for a classic example would be your mouse clicks. Okay, so if you click a button on a web page, maybe there are actually multiple listeners to that button. So what I mean by listeners is there are some web pages that if you click on a button, maybe a carousel pops up somewhere, or maybe the browser sends out a request to a server, and let's just assume that there's a button that does three things. Okay, so when you click on that button, what happens? All the three workers that will carry out the tasks when the button is clicked will all get notified. So their job is to actually, pick things up and try to get things done. All right. So that is actually a way that concurrency happens. But in the terms of the browser uses what we call asynchrony, so asynchronous calls. So in a sense, that is concurrency. If you have experience with languages like JavaScript or Node.js, that's basically how Node does its own concurrency by using asynchronous calls. So it sort of registers these things that get executed later. Okay, so it's not like those things are done, like by three different computers or maybe by three different processes. No, it is queued and they are done, in a specific in an order that is not really organized. Okay, so it could be the first guy goes. So now because the web request has been sent out, the computer moves on to do the other one, maybe printing to console. Okay, so now whenever the web server comes back with a response, it now goes back to continue with that other task. So that is basically how concurrency works, on the browser. And it's the same thing with Go. Yeah, so it's the same thing but a different model, as you're going to see. Okay, so hopefully that makes sense. Now, Go has a huge support for concurrency, and it makes writing concurrent code really easy. Concurrency was built into Go language itself. There are so many languages that you require to use an external package or some different engine to make concurrency really possible. But the designers of Go had concurrency in mind, so it was really built into the language, and it's very easy to use it in your programs. So they have the context, the concept of what we call Go routines. Okay, so don't be afraid of this name. Trust me, the first time I heard this name, I was really scared. I'm like, what? What is a Go routine? This has to be really hard and difficult. I mean, I would never understand this. Oh, I'm doomed. I shouldn't have taken this Go programming language in the first place. Calm down. Trust me, this will be it will be surprisingly easy, really easy to create a Go routine. Okay. However, the only challenge that comes with concurrency is not the maybe the Go routines themselves, but the concept of concurrency. How would you think about concurrency itself? How to reason about it, and how to really make useful programs from them. Okay. Go routines are lightweight threads, all right, that can also be referred to as green threads. So, first of all, what the heck are threads? All right. So, before you understand what a thread is, you have to understand what a process is. Okay. So, is a process is basically a program in execution, like I wrote down here. So you can imagine I have how many programs do I have running? 1, 3, 4, 5, 6, 7, and even in some of them I have 2 different VS codes running here. So I have like what 8, 9 processes running right now. So any program that you start in your new computer system, it creates a new process. So your OS, your operating system creates a new process from every program that you execute. Now, inside of these processes is what we call threads. Okay, so threads are somewhat baby processes that actually execute the code of your program. So the threads are what holds the tasks and the procedures that are going to be executed on your machine. All right. So processes are made up of um, threads, just like OS operating systems are made up of processes, and processes are made up of threads. All right. So the operating system manages the process. So it gives it the memory access, gives it the CPU time, gives it things like power, everything that makes your programs work. The OS manages those resources, the RAM, the hard drive, everything, the battery, all of those things. The OS manages them. Who gets allocated what? But inside of your process, threads now share those resources that were allocated to your process. So you can imagine if there is a particular memory that let's say a memory that was assigned to your process, and now you have multiple threads accessing them. You can imagine that one thread could come and remove something from memory, and another thread is expecting to have that thing in memory, and when it doesn't find it, that is where problem starts. Okay, so this is just one of those things that makes um, working with concurrency, working when programming concurrent systems difficult, because programs can be really complex, and when you start trying to execute so many things concurrently, it actually becomes it can become really difficult to handle. Okay, so but Go has some really nice concepts that makes all of these things a breeze, as you are going to see. So Go routines are really light, all right, light in the sense that a thread can be about 1 megabyte, but a Go routine is just 2 kilobytes. Yeah, really light. So you can create millions of Go routines, and that's actually one of the features that makes Go really faster than a lot of programming languages out there. Concept of Go routines. All right. So now, if you remember, when I was talking about the browser's asynchronous way of handling concurrency, I mentioned that that's things like events. You hear events. So events is one way, like I said, and then you see things like process threads that I've already explained. Right now, you have a process and have multiple threads, which means you can send multiple threads on multiple things to do at the same time. That's a way of doing concurrency. And then you have callbacks and promises. This is very, very famous in the Node.js community, where every asynchronous call returns a promise or requires a callback for that to happen. Okay, so now Go implements what we call CSP, communication sequential process. So CSP was actually written, is a theory written by Tony Hare. So you can Google this. There's actually the white paper is actually online, so you can read it and see the protocol that actually defines what it is. So this protocol focuses on what we call interactions between components in a concurrent system. So this is done in what we call message, like in a message-based format. Okay. So remember when I pointed out that a process that is running a program gets a particular data in memory assigned to it, and then you have multiple threads making use of this data, and one thread tries to, or maybe removes that data in memory. The other threads, or maybe another thread tries to use it, and then it doesn't exist anymore because it doesn't know what happened to it. There's going to be a problem. Your program will probably crash and cause things like memory leaks, which exposes your programs to security flaws. Okay, so but this is that form of concurrency is what we call communicating by sharing memory. So when threads are independent, okay, so when they are doing things, you might need a way to provide context so that what they are doing will make sense to you, because we're not doing exactly different things, like absolutely foreign things. We are doing a task that when brought together makes sense to our program, right? So we in that kind of concurrency, this communication is achieved by sharing memory. So they are all created in the same memory space, so sort of in the same memory where everybody can read what they need from memory. So that has its problems because somebody can remove something from memory and others cannot find it. All right, but shared memory, it works for some systems, and some people have actually figured out how to make it really, really work for them, and it's good. I've used it in languages like Rust, and it's really interesting. All right, but there is another way of achieving this. That is where the CSP model comes into play. So instead of sharing memory, why not just communicate? Yeah, why not just communicate? So instead of putting that data in memory, why not send those information through a channel? All right, or maybe through a space, through some sort of a message, through some sort of way of sending a message. Let's say I want to give this particular thread an information. Instead of sharing it to everybody, I just send it to that thread as a message. So this is where channels now come into play. So channels are they are a communication mechanism that lets Go routines send values to another Go routine. Okay, so don't worry. In this, I think what will happen is I'm going to just talk about the theory in this video, and in the next video, I'm going to now jump straight into code, and then we can see what Go routines are, how to create them, and how we can make use of them. All right. So channels are basically that's all what channels are. All right. So you can think of them as a route. So maybe think of a tube where trains pass from city to city. That's just what it is. So it connects multiple Go routines. So a Go routine can pass a message into a channel, right? And another Go routine can now read the message from that channel. And you can have millions of Go routines communicating over a channel, passing messages, receiving messages from channels, and that way they can, access the data they need to complete what they are doing. All right. So I think that's that for this. If we'll have different types of so to create a Go routine, we use the Go keyword. Okay, so we'll see that when I in the next video when I actually jump into the examples. So to create a channel, we use the make function and specify the type that we want, and this will return an instance of a channel. All right. So yeah, these are the mechanisms of how a channel works. We'll all see that in the next video. We have buffer and unbuffer channels. I'll show you examples of this. And the buffer channels are channels that have a capacity. Okay, if you remember when we are creating maps, we were and the arrays, we could specify capacity and of our arrays, and this make function will make sure that our created values do not exceed those capacity. So buffered channels are channels that have a capacity that it cannot exceed. All right. So I think that's that for this video. So in the next video, we're going to dive into writing Go programs with channels and Go routines. See you then.